afternoon. I'm Wenli from the Hong Kong University of Science and Technology. And today I'm going to talk about our research, the image-based automatic modeling and performance evaluation for house plans in the early design stage. And we also call it image-to simulation. And so first, imagine if you are an architect. You are using the generative model to generate hundreds or even thousands of the flat layouts. And this technology is amazing for its creativity and efficiency. But with so many options, how can we determine which one is the best, and how can we evaluate all the flat layout images? And when we think about how to make a building better, maybe the performance is a key factor, which is crucial for the sustainability. And we can see the buildings and construction account for 34% of the global energy demand, especially in the residential sectors. And a lot of sustainability assessment criteria also mention the performance evaluation, and especially the energy consumption, daylighting, and thermal comfort. And when we try to conduct the performance evaluation, usually we use this simulation ecosystem, the software like the just mentioned, the Rhino, Ladybug, the Energy Plus or Radiance to conduct the simulation about daylighting or energy consumption. And this ecosystem may include two parts. The first part is the design drawings, and secondly, these all design drawings can be imported into the simulation tools automatically and as the simulation model. But the problem is for the generative design, instead of Revit or CAD format, the images is a more universal format in the generative AI models. For example, here we can see on the left, here the R-plan dataset, which is one of the most widely used dataset in the generative design domain. And this dataset contains 80,000 images about the flat layouts. And each image includes several channels to represent the room number, room type, and other informations. And for this image dataset, it can't be imported into the simulation tools directly. So there are some current methods to solve this problem, like the Venus, but still has some limitation. And first one, because in the original dataset, there are some inherent errors, like here, marks in red, these pixels. They are inherent between all the channels. And the second thing is when we try to process the diverse wall thicknesses, the current method has some limitation. They can process some case, and also has some limitation about the window and balcony definition. So here comes to our research objective, to develop a new method to convert the image format into the simulation models. We call it the image-to simulation algorithm to improve the capability and accuracy. And here is the whole workflow of our algorithm. It includes 6 steps. And the idea is initially we have the flat layout image as the input, and the output is the simulation-ready coordinates of all the room and window vertices. And in this 6th step, the 3rd step is a key important thing to assign the non-room pixels to process the walls part. This part is quite important because when we import it to the simulation tools, the walls part is to be identified as the exterior wall or the interior wall has quite impact on the performance because their attributes is quite different. So for this step, our method is like here is a visual process. And first we have the room mask from the initial image, and we can get some segments of part of the exterior wall. And third thing is we add some points to emphasize the connection sequence. And finally, we can get the entire exterior wall. And this method really on the room mask instead of the original information from the dataset, the exterior wall information. So we can avoid the inherent errors. And next step, the step 4, is quite similar. We can expand the room mask by a specific distance and to fill the worst part. And here is the results. On the left, you can see the original image from the dataset, and on the right is these are our converted simulation models. And of course, we have some field cases. For example, there are some gaps, overlaps, but it's quite small, so the impact is very minor. And we also compare our method with the current method values. For all the images in the upland dataset, the over 80,000 images, our successful rate can improve by 8%. And until now, we have all the simulation models. So what we can do next? Here we provide a practical application to train a surrogate model to predict the energy consumption. And here is the whole workflow, and we can see our image-to simulation play a key role in the steps marked in red. And we test several models and also develop our own model. And all the models can achieve a high accuracy. So with more data, we can get the energy label. We can improve our accuracy of the surrogate model. And to sum up, our research first provide an image-to simulation algorithm to improve the capability and accuracy. And secondly, we can provide over 54,000 simulation models for future research. We can provide the image and the energy labels. And the third thing is we provide a practical application in the surrogate model developing. And of course, we have some limitations, like we still have some field cases, and the window setting and the word setting is limited. We can improve and add more method to the conversion process. And that's all. Thank you.